The building block of our digital world is absolute certainty. A choice is made, a 1 or a 0. The coin comes to a dead stop on heads or tails. We string these absolute choices together into a flat sequential line to process information. But nature doesn't actually work in absolute flat lines. At the subatomic level, the universe operates in a complex state of overlapping possibilities. If classical computing is a coin that has already landed, quantum mechanics is a coin perpetually spinning in midair, where both heads and tails exist at the exact same time. This overlapping reality is known as superposition. To measure these overlapping states, researchers currently rely on massive dilution refrigerators, like the one seen in this photograph, cooling processors to near absolute zero. That extreme hardware requirement creates a severe physical bottleneck, effectively locking independent researchers out of quantum experimentation. To make quantum computing accessible, we need a method to calculate multidimensional reality that works within the constraints of standard hardware. Enter QxBin, or Q-binary. It is a theoretical framework designed to replace the standard flat string of binary data with a spatial, multidimensional quantum chain. This technical sketch shows the creator's initial vision. The data expands outward from a single line into the circular nodes mapped out beneath it. Looking at the mathematical breakdown, the system deconstructs whole integers into fractional bases. Instead of absolute ones or zeros, we use ratios representing directed contributions. By raising these fractions to positive and negative exponents, variables n and m, it constructs a functional coordinate system. The result is a binary probability matrix. It takes flat line data and gives it depth, height, and probability weight. This creates a literal map, plotting overlapping states of quantum superposition into fixed coordinates that a standard machine can process. QxBin effectively translates the infinite blur of a spinning coin into a highly organized, mathematically rigorous grid. Curious, but mapping out a probability grid on paper is only half the problem. How do you physically input these multidimensional coordinates using classical hardware? A standard mechanical keyboard switch is strictly binary, either fully pressed down or fully released. The physical bridge comes from Hall effect sensors, found in specialized magnetic keyboards designed to detect analog variance. A Hall effect sensor measures the exact distance and magnetic field strength of a key press. It captures the analog nuance and specific pressure of a finger. This hardware captures the physical wobble and hesitation of a real-world action, feeding those exact probabilities directly into the matrix, all while sitting at a room temperature desk. And the math holds up. This section of the empirical validation demonstrates how the theoretical probabilities of the QxBin matrix match the outputs of standard quantum reference simulators. This validation provides a foundation for personal qubit simulation, or PQC. It means we can use highly tactile, grid-based systems, much like the layout of this vintage punch card, to record and process the spherical representation of a quantum instance. As the creator noted in this handwritten essay, it is a strange but powerful translation. It's like building an airplane using the mechanical analogy of a horse. By expanding beyond a flat line and treating data as a multidimensional matrix, this framework circumvents the billion-dollar hardware barriers of modern quantum research, making the underlying logic accessible to anyone with a computer.